Einstein's Relativity, the Special Theory and the General Theory, Chapter 2, The Frame of Reference. New Modern Translation 2024. Albert Einstein and Harry Yoon, Translator. Introduction, Chapter 2. Relativity, the Special and the General Theory, a Popular Exposition, was the first book, and in fact the only book, by Albert Einstein specifically written for the popular non-physicist audience on the theory of relativity. This book is not, however, for the faint of heart. It goes through some of the most essential ideas of both special and general relativity, and it touches on many fundamental concepts, which you cannot find in most textbooks on relativity. Although mathematics is kept at minimum, it is, in many ways, a much more difficult book than those they use in college physics classes. If you are genuinely interested in understanding relativity at a high level, and yet paradoxically at a deeper level at the same time, rather than, say, just learning how to calculate time dilation and length contraction using the Lorentz-Einstein transformation equations, then we highly recommend this book written by Einstein himself, which is full of great insights, if you can spot them. However, we are by no means trying to discourage the casual readers from reading this book who want to just get something out of this book by quickly going through it, or to get as much as possible in the limited time they have. In fact, that would be a great way to get exposed to relativity, using Einstein's book. But these books in this single chapter edition series are specifically created for the people who want deeper understanding of both the special theory and the general theory of relativity, without having to learn difficult high-level mathematics. To those people, we recommend to read the Einstein's Preface first, if you haven't already done so, which is included in the beginning of all single-chapter booklets. Understanding relativity, truly understanding relativity, requires patience and some time and effort, regardless of your background. This is the second installment of the series, and it includes Chapter 2 and only Chapter 2, from the book Einstein's Relativity, the Special Theory and the General Theory, New Modern Translation 2024. The title of this chapter, or section as the book was organized in the original German edition, was The System of Coordinates. We changed it to The Frame of Reference since this term is more commonly used in modern physics. These two terms are more or less interchangeably used, however, depending on the context. Likewise, in general, we took a liberty to do liberal translations throughout the book, rather than following the original German text too literally. For anybody who prefers more literal translations, the official 1920 translation, with some revisions, is available in public domain for free. One final note. For those readers who are familiar with basic concepts like coordinate systems and reference frames, and who think that this book starts too slow, we still recommend to quickly go through the first few chapters. There are always some hidden gems in Einstein's writings, technical or otherwise. He had rather unique and sometimes unorthodox views and opinions, even on the subjects that many people would have considered mundane or too simple. Original Preface by Einstein. This little book is intended to give the most accurate insight into the theory of relativity, as far as possible, to those who are interested in learning the theory from a general scientific and philosophical point of view, without having to master the mathematical apparatus of theoretical physics. The book assumes that the reader has completed the equivalent of the high school graduate level education. Furthermore, despite the fact that it is a short book, reading this book will require a lot of patience and willpower on the part of the reader. The author has made every effort to present the main ideas as clearly and as simply as possible, and generally in the order and context in which they actually arose. In the interest of clarity, it seemed inevitable to me to repeat myself as often as necessary, without the slightest regard to the elegance of the presentation. In fact, I conscientiously followed the doctrine of the brilliant theoretical physicist Ludwig Boltzmann, that elegance should be left to the hands of tailors and shoemakers. I do not believe that I have withheld from the reader the difficulties which are inherent in the subject matter. On the other hand, I have deliberately ignored the formal physical foundations of the theory, empirical or otherwise, so that the reader who is not entirely familiar with the subject of physics may not end up like the lost explorer who cannot see the forest for the trees. I hope this little book brings you some happy hours of inspiration. Albert Einstein, December 1916. Chapter 2, The Frame of Reference. Relying on the physical interpretation of the geometrical concepts such as distance, as explained in the previous chapter, we can now determine the physical distance between 2 points on a rigid body in practice, e.g., through measurements. For this purpose, we need a rigid rod with a fixed length, interval s, that we can repeatedly use as a standard measuring stick. If A and B are 2 points on a rigid body, then a line, or more precisely straight line, connecting these 2 points can be constructed according to the laws of Euclidean geometry. Starting from one point A, then, we can remove the interval s along this straight line as many times as necessary until we get to the other point B. The number of the removal operations performed is the numerical measure of the total distance AB. This is the basis of all measurement of physical length. Any spatial description of the location of an event, or of an object, boils down to specifying the point on a certain rigid body of reference, with which that event or object coincides in space. This applies not only to scientific description, but also to everyday life. If I say, for example, that an event occurs at the location, Potsdam Square in Berlin, it specifically means the following. The Earth's surface is the practically rigid body to which the location refers. On this surface, Potsdam Square in Berlin is a particularly marked location with the given name, and the event coincides in space with this particular location. This simple method of specifying a location, however, can only be used with the points on the surface of a rigid body. This method is further limited in that it is dependent on the presence of specifically marked and named places on this surface. Let us see how we can free ourselves from these two limitations, using the sheer power of our imagination, without altering the essential nature of our location specification method. Suppose, for instance, that a cloud is hovering over the Potsdam Square. We can determine its location in the three-dimensional space, in relation to the surface of the Earth by erecting a pole vertically on the square, so that it reaches up to the cloud. The length of the pole measured with the measuring stick, e.g., the height to the cloud, together with the location of the base point of the pole on the Earth's surface, is then a complete location information of the cloud. Based on this example, we can now see how to go about creating a more refined method of specifying a location, anywhere in general. The rigid body to which the location refers is extended in such a way that the point to be located is reached by the extended, imaginary rigid body. To specify the location of a point, we use numbers, e.g., the length of the pole measured with the measuring stick in this example, instead of the names of particular places. The height of the cloud can still be indirectly measured, even if a pole has never been really erected to reach the cloud. In this case, we can determine how long the pole would have to be made to achieve this by taking optical photographs of the cloud from various points on the ground and using the propagation properties of light. This consideration shows that it will be advantageous in formulating spatial location descriptions if we can just use measurement numbers, regardless of the existence of any marked or named points on the rigid body of reference. Analytical physics achieves this by making use of the Cartesian system of coordinates. A Cartesian coordinate system consists of 3 rigid and flat walls, or planes, with no thickness, that are perpendicular to each other and connected to form a rigid body. The location of a point, or of an event, in relation to the given coordinate system is essentially described by the specification of the lengths of the 3 perpendiculars, or coordinates, x, y, z, which are cast from the point on those 3 plane walls respectively. The lengths of these 3 perpendiculars can be measured in principle through a series of operations with a rigid measuring stick, in accordance with the laws and methods of Euclidean geometry. In practice, the rigid planes which constitute the system of coordinates are generally not available. Furthermore, the values of the 3 coordinates are not actually measured using measuring sticks, but rather they are determined indirectly. Regardless, in order not to make the results of physics and astronomy to dissolve into obscurity, the physical meaning of the location information must always be sought in accordance with these considerations. To summarize, every description of events in space makes use of a rigid body to which such events can be spatially referred. This relationship, or mapping between space and a rigid body of reference with an attached coordinate system, or frame of reference, presupposes that the laws of Euclidean geometry hold for intervals, or distances, in which the distance is physically represented by two marked points on an extended, rigid body. Translator's notes. In this second chapter, Einstein introduces the coordinate system as an analytical tool for doing geometry, which we owe to René Descartes, among others. Many readers of this book should be already familiar with the basic ideas of coordinate systems. In physics, the coordinate system is closely related to the reference frame, which is one of the most fundamental concepts in mechanics, as well as in other branches of physics. A quick summary. In order to measure distance in practice, we need a rigid rod of a fixed length, S. Then, given 2 points on a rigid body, A and B, we connect the 2 points with an imaginary straight line and try placing the rod repeatedly along this line, starting from one point A until we reach the other point, B. The number of the repeated placements of the rod essentially represents the distance. That is, if it takes n repetitions to go from A to B, then the distance d between these 2 points is d equals n times s. In order to specify a location, we will need to specify the location with reference to a rigid body. For this, we attach an imaginary three-dimensional Cartesian coordinate system to the rigid body, in such a way that its two coordinate axes lie on the surface of the body, and the remaining axis is vertically extended from the surface. Then we can specify the three-dimensional location of an event, or of an object, by using three numbers or coordinates x, y, z, which are the vertical or perpendicular distances from the three coordinate planes of this Cartesian coordinate system attached to the given rigid body of reference. These distances can be measured in principle, although not always in practice, using the method defined earlier. Hence, all locations can be associated with three coordinates with respect to a body of reference and its associated Cartesian coordinate system. In physics, we use the term frame of reference to refer to such an extended, rigid body of reference equipped with a Cartesian coordinate system. Note that this method of specifying a spatial location presupposes the validity of the laws of Euclidean geometry in the real world. In particular, it assumes that the physical distance between 2 points on a rigid body corresponds to the distance in Euclidean geometry. Distance. Everybody knows what distance is. Or at least they think they do. Einstein was, however, the first person that challenged our very notion of distance in over 2,000 years of our scientific pursuit, which began in ancient Greece. What is space is still an open question in physics and philosophy at the fundamental level. Einstein defines the distance in an operational way. That is, he defines a physical distance in terms of how to measure it. More specifically, the distance between 2 points on a rigid body of reference is defined to be the number of times that a standard measuring stick can be laid along the straight line between these 2 points. Note that the essential concept of distance does not depend on the length of the measuring stick used. Measuring distance in physics, according to Einstein, is simply counting, with a particular but largely arbitrary choice of the measuring stick. In the first 4 chapters, Einstein is carefully laying a groundwork even before we start discussing relativity. The definition of distance given by Einstein, for example, may not be unique or even the best. But without such a concrete definition, which is reasonable enough that we can all agree on, all following discussions will suffer from vagueness. A rigid body of reference. It may appear to some readers that we seem to always say that nobody understands nothing. But that's because there are different levels of knowing and different levels of understanding. If you really go deeper and deeper, you will realize that our knowledge and our understanding is really fragile, at the most fundamental level. For example, many of the readers who had some education in physics should be familiar with the concept of reference frames. Of course, every physicist knows what the reference frame is. But if you really think about it, do you really know what it is? What's the difference, for example, between space, e.g., in the context of general relativity, and a reference frame? Why is it that we can attach a coordinate system to a reference body frame, but not directly to space? In this book, Einstein introduces the concept of reference frame using the physical but idealized rigid bodies. This way, the abstract concept of reference frame becomes more concrete and real. All locations need to be described in reference to a specific physical rigid body, such as the ground or a moving train, or its generalization, reference frame. The Cartesian system of coordinates. We all know the story of Copernicus and Galileo, and how the scientific revolution began in the 16th and 17th century in Europe. But one thing that we are not very familiar with is the fact that the mathematical revolution also started at about the same time. People like Fermat and Descartes, as well as Newton and Leibniz, played important roles in creating modern mathematics after almost 2,000 years of status quo, i.e., Greek mathematics such as Euclid's geometry. Most of the progress during this period, primarily in the area of algebra, came from outside Europe, especially from the Islamic world. If we are to pick a single most important event in the history of mathematics, then we will pick the invention of analytic geometry in the 17th century, which is largely credited to the French philosopher René Descartes. Descartes introduced coordinate systems into geometry, now known as the Cartesian coordinate system after him, and as the saying goes, the rest is history. Algebraic geometry, or analytic geometry as they are now called, were so powerful that they completely changed geometry and mathematics in general. At this point, nobody does classical geometry a la Euclid, at least in physics. For virtually every geometric problem, we now use algebraic or analytical techniques, which was made possible essentially by the introduction of coordinates. If any of the readers wants to learn more physics, especially relativity, then they will have to learn geometry, which really means learning modern analytic geometry, including differential geometry. Greek geometry. Speaking of classical geometry, here's an interesting geometry problem if anybody is interested. In this chapter, Einstein states that the physical distance can also be indirectly determined as long as its method is practically equivalent to the method and principle of measuring distance directly, using a chosen standard measuring stick. The height of the cloud can still be indirectly measured, even if a pole has never been really erected to reach the cloud. In this case, we can determine how long the pole would have to be made to achieve this by taking optical photographs of the cloud from various points on the ground and using the propagation properties of light. Based on this description, how would you go about measuring or estimating the distance to the cloud? There can be more than one way to do this. We will leave this problem to the readers as an exercise. Incidentally, the first person, on record, who solved this kind of problems was Thales of Miletus, who is now considered the father of Greek philosophy. Thales lived circa 6th century BC, in the city-state of Miletus in the Ionian region of ancient Greece, now part of Turkey. He is also considered the father of Greek mathematics. One of his most important contributions to geometry is known as the Thales theorem, which predates the Pythagoras theorem. Briefly, the theorem states that any triangle inscribed in a circle with one of its sides along the diagonal of the circle is a right-angled triangle. This theorem essentially gave rise to trigonometry, which is one of the most basic building blocks of modern mathematics. Thales also seemed to have known various basic concepts of geometry, such as similar triangles and congruence, etc. According to a legend, when he was in Egypt, he measured the height of the Great Pyramid of Giza. He also knew how to estimate the distance to a ship on the sea, e.g., without laying a ruler on the water. Again, we will leave as an exercise to the interested readers as to how he would have done it. What's next? So far, Einstein introduced two important concepts in the first two chapters: the rigid body of reference and the system of coordinates. These two concepts are related, and they are pretty much interchangeably used in various different contexts. However, when in doubt, we will always have to go back to the physical rigid body under consideration. At least, that is the interpretation of the translator. The more modern conception, the frame of reference, seems to lie, conceptually, somewhere between these two concepts. In the next chapter, Chapter 3, we will review the fundamental concepts of space and time and that of motion, as they are used in classical pre-relativistic physics. Chapter 3, Space and Time in Classical Mechanics.